turn it over to David Madigan. uh, I'd like to, David Madigan uh, recently moved to Northeastern University from Columbia University. At Columbia, he was, one of the driving forces behind the Observatory for Healthcare and Data Science and Informatics. And following on that work, which is, one way to think about it is how to produce reliable and causal inferences from very complicated data sets that all speak to the same question, but they are hard to have them to work together. So he's an expert in this sort of area of research, and I think he's going to tell us about his more recent work on Legend, which is another project in that spirit. David, I'm going to turn it over to you. Thank you for being here.
Super, thanks, Edo. I'm very happy to be here, and slight change of direction here. Unlike my fellow panelists, and I'm not going to focus entirely on COVID, although I will touch on it in a few minutes. So what I'm about to talk about is, or make remarks about, is a body of work that's been going on for 6 or 7 years under the auspices, as Edo alluded to, of a collaboration called Odyssey. And anything and everything I'm talking about you can find on the Odyssey website. The URL is there. So I'll come back in a few minutes to say some more about Odyssey, but I want to start in a different place. So next slide, please. Thank you. So what I want to talk about primarily is, if you will, a kind of a genre of work or of research in the healthcare space. So medical journals are full of papers like this one. And I'm not picking on this one in particular, it's just that it's a very good example of the genre I'm talking about. So what's going on here is a group of authors who are studying essentially a causal inference problem in the healthcare space. They're comparing different drugs, 4 of them there, apixaban, dabigatran, rivaroxaban, and warfarin. These are blood thinners. And they're looking at the risk of major bleeding in patients with atrial fibrillation, a comparative analysis of this risk across these 4 drugs. So the analysis they conducted it in a very large US-based claims database, insurance database, that has, of the order of 100 million patients represented in the database. Much of the evidence that is guiding the practice of healthcare as of 2020 is coming from studies like this. It's no longer coming from randomized trials. So we have access to, we as a society, as a globally, have access now to massive scale electronic health record data, be they administrative claims databases like these good folks are using, or electronic health records that are generated during the practice of healthcare. But we now have multiple years, as I'll get into some more specifics in a few minutes, multiple years of data for hundreds of millions of people around the world, and the enterprise of generating reliable evidence about the practice of healthcare, to guide the practice of healthcare from these databases, is a massive enterprise, globally. So it's very important. This is where most of the evidence is coming from. So my basic point that I'm going to make is that, in a sense, the way we go about doing these studies is pretty messed up. Not to get too technical at the outset. There are real problems with the way we do this. So I want to zero in on a few of these problems. I could talk for hours about it. I won't. And then I want to describe what I think is perhaps a better way of generating reliable evidence from these large-scale databases. But before I do, let's just look at this study a little bit more closely. So, as I said, they're comparing 4 different treatments in a cohort of patients with atrial fibrillation, and the outcome is major bleeding risk. The paper, like all papers of this type, it produces a statistical artifact. So in this case, for instance, they're looking at comparing matched rivaroxaban patients, that's one of the drugs, as compared to apixaban patients. So they're doing a pairwise comparison between 2 of the drugs in here. And they're saying that the rivaroxaban patients had essentially a doubling of the risk. They were twice as likely to have a major bleed than the apixaban patients. And there are other conclusions in this paper, that's one of them. And that is exactly the kind of result that then guides the practice of healthcare in terms of which drug would you prescribe to which patient. Crucially here, they produce a statistical artifact. It's a 95% confidence interval. And the basic idea here is, what a physician or a patient or a decision maker would look at that and interpret that to mean that 95% of the time an interval like this contains the true causal effect, right? The true effect size, which we could argue about what that means, but let's just run with that. So in this particular case, the interval goes from 1.4 to 2.4, and crucially, it's north of 1, so it doesn't include 1. So a typical interpretation here would be that this is solid, this is statistically significant, and you can proceed as if there really is an effect here. Now, there's a problem, which is we don't actually know what the coverage of that interval. I've been talking quite a bit about coverage in the predictive context. Here I'm talking about coverage in the inferential context. But we don't actually know whether this interval covers the truth 95% of the time, or 50% of the time, or 100% of the time, because there are basic simple assumptions that go into the underlying math here, which we know are false. So the basic assumption is that one of them is that you have an unbiased estimator. We know that's not correct in these kinds of studies. There are many sources of bias that bedevil these kinds of studies. So work that I've been involved in, and many people have been involved in, to try and establish the operating characteristics of studies like these suggests that the true coverage is probably in the 40 to 60% range. It's not like 93% or 96%. It's way off, right, in practice, almost certainly. So in other words, the interval, a 95% interval here should probably look something more like 0.5 to 4. So we're proceeding as if we've nailed it, we know what's going on, when in actual fact, we really don't, because there's no basis on which to assess the coverage. Next slide, please. So that's problem number one. We think it's 95% coverage. It isn't. Kind of demonstrably, it's not, and therefore decision-making pursuant downstream from this is sort of intrinsically unreliable. Next, please. Another problem with these kinds of studies is they're not necessarily pre-specified. You actually have no idea what these authors did, what the process was that yielded this egg, if you will, that they lay, in the paper. And in particular, you don't know if the analysis that they're reporting here was pre-specified. So did they try 20 different analyses and choose the one they liked? And it's not necessarily nefarious. They might have thought it was the best analysis, but there's no suggestion in here that it was pre-specified. That's typical of these papers. Next slide. Is it reproducible? I guarantee you it's not. Meaning, if a second group of authors set out to run this analysis and reproduce these numbers, they couldn't. And there are many reasons for this. It's a complicated, interesting societal problem. But let me give you one little kind of insight or snippet as to why you can't reproduce a study like this. There's a statement in the paper, very typical of this, that talks about baseline patient characteristics that included age. Okay, that's fairly well defined, maybe, although you don't know whether they categorized it or not. Gender, geographic region, how defined? Clinical characteristics, and baseline medication use. Good luck trying to reproduce that. And it's essentially completely impossible. Next slide. Is it generalizable? Does this apply to me? Does it apply to you? So this model, this analysis was conducted in a US-based claims database, so people who are insured in the United States. Does that apply to people in Korea? Does it apply to non-insured people in the United States? So the major questions about the generalizability. Next slide. In essence, the process right now that produces these kinds of studies is entirely kind of artisanal. It's like it's an arts and crafts kind of a business. You're relying on the skills and the scientific kind of prowess of the folks doing the analysis. It's like, and I've literally heard this. Trust me, I'm a good analyst. I know what I'm doing. It's a good result. So it's a very unsatisfactory state of affairs in terms of generating this is the evidence that's guiding the practice of healthcare. It's really quite scary. Next slide. So I hope I've given you a flavor of why the current state of affairs is in very many ways problematic. So now I want to switch gears and talk about a new approach that we call Legend, that has been developed in the context of the Odyssey collaboration. I don't for one second think this is the last word or the best way of doing this, but I think it has characteristics that are desirable, and I'm hoping it leads to a significant improvement in the way we generate evidence going forward. So what we sought out in developing a new approach is we wanted something that was reproducible. So you could go back and literally perfectly reproduce any analysis we do. We wanted it to be systematized. So none of this artisanal, I decide to adjust for this and I decide to exclude that and so on, but a systematized approach that is essentially automated and done at a very large scale and entirely open source. So that the code is available, the protocol is available, completely pre-specified analysis is what we sought out. A key aspect of the approach, or a key characteristic, is the use of negative controls. So this is not a new idea, it's been around for a long time. The Legend studies are doing it perhaps on an unprecedented scale. Basic idea is very simple. Let's imagine we're studying drugs, it extends to other medical interventions. But a negative control is a drug and an outcome where it is, quote unquote, known that there's no causal association. Okay, so there's a bit of a circularity to this, which is if we don't know how to do this causal inference, how do we know that something doesn't cause something else? Suffice it to say that we have developed a very large scale, algorithmically driven approach to identifying negative controls. We could have a good argument about how good it is, but it's at least a step in this direction that is transparent and reproducible. We derive these negative controls from very large scale literature crawls, from structured analysis of product labels, and also analysis of so-called spontaneous reports. Therein lies a lengthy story in and of itself. We identify negative controls. This enables us to produce what we refer to as empirical p-values. So rather than statistical artifacts that rely on wildly unrealistic assumptions, we simply generate statistical artifacts from basically how well do these methods do on the negative controls, where we quote unquote know the answer. It's a long story, and I'm happy to provide references to the various papers that describe it in detail. We also utilize positive controls, which are drug outcome pairs with a known effect size, and our current approach is to simulate these using very large scale models that enables us to produce calibrated confidence intervals. I would describe this as a work in progress. There's a lot to be done. Next slide, please. So let me just give you a quick flavor. I don't have a huge amount of time. Let me give you a quick flavor of this approach in action. So in 2017, the American College of Cardiology and other organizations produced new guidelines for the management of hypertension. Hypertension is extremely common in this country and around the world. This guideline is hugely important in terms of the actual practice of cardiologists and physicians in general in managing hypertension. 56 pages, 106 recommendations. They very carefully discriminated between recommendations that were expert opinion, and then they had gradation from all the way from expert opinion to guided by randomized controlled trials. Next slide, please. Next slide, please. Thank you. So in this guideline, they considered, if you look at all the different treatments, pharmaceutical treatments they considered for hypertension, there were 39 different drugs that they considered in this analysis. They formed different drug classes, but 39 different ingredients. And the slide there on the left, or the circle on the left, just shows you how common these different drugs are in a particular database in the United States. So it's kind of the Wild West in terms of the array of drugs that's used for hypertension. Next slide, please. So they considered 39 treatments in the guideline. 58 different outcomes of interest were mentioned. So these range from bad effects of these drugs, adverse effects, to good effects of these drugs. There are 58 of them. Next slide, please. The 39 drugs are arrayed around a circle here on the top half of this slide. And what we've filled in here is we've put in a line inside this circle for every head-to-head comparison of a pair of drugs for which there is evidence from a randomized trial. So as you can see, there's a huge dearth of evidence. And indeed, many of the recommendations in the guideline are based on expert opinion, what experts think, rather than actual evidence. So our goal in this, in the LEGEND study we did on hypertension, it's one of several we have done, is to basically go from the left-hand side to the right-hand side. We wanted to fill in the circle and generate reliable, reproducible evidence with known operating characteristics for every possible pairwise comparison in this circle. You can't actually do all of them because even though we're dealing with very large-scale databases, you run out of data for many of the comparisons for the less widely used drugs and the less common outcomes. But in any event, it's over 10,000 comparisons. We conducted this study globally. So what we did is we did a head-to-head comparison of every pair of drugs, that's 39 choose 2, for all 58 outcomes, using negative controls and positive controls in an array of databases that are listed there, that they don't cover the entire globe, but it's a few 100 million patients in different parts of the world. So US, Japan, Korea, and Germany included in this. The full Odyssey network, I'll get to it in a second, I'll talk about it briefly, is bigger than this, but this particular study we conducted in these databases. Next slide, please. I think there might have been a second slide there. There we go, thank you. So here are the results, so to speak. So in the end, our study produces 1.3 million estimates. So we're doing what some folks refer to as the all by all, right? All pairwise comparisons of these hypertension treatments. We're filling in the circle, right, for all 58 outcomes. And let me orient you quickly with this picture. The horizontal axis is the point estimate, where a hazard ratio of 1 is the neutral value. The vertical axis is the standard error. And these dotted lines give you that's the boundary for classical statistical significance at the 5% level. For this analysis of that 1.3 million estimates, 83% of those confidence intervals include 1. It's not 95%, but it shouldn't be 95% because one assumes that many of these are real effects. But every single dot on this study is backed by full automated diagnostics and actually a full paper. So we can generate 1.3 million scientific papers, and have done, that describe every single dot in this picture. Now, that's what it looks like, basically, if instead of cherry picking and studying one thing in an artisanal way, basically fiddling around and producing a result, this is a systematic, automated, complete analysis of hypertension drugs for these 58 outcomes. Next slide. Keep that picture in your head while I go to the next slide. That's what the literature looks like. So if you do a crawl, which we've done several times, of the literature of observational studies, that's what it looks like. There's disastrous clustering just under the 0.05 level. This is p-hacking, right, that we all know about and talk about. So go back a slide, please. Actually, if you could just go backwards and forwards a couple of times, please. That's what it looks like when you don't have, you're not doing pre-selection and fiddling around. That's what the literature should look like. Go forward a slide. That's what it actually looks like. We have a problem. We have a real problem. Next slide, please. Oh, sorry, I should have said it before I get there. In the previous slide, 85% of the results were statistically significant. When you do this more honest, I would claim, analysis, it's the other way around. 85% are not statistically significant. I invite you to look at that. It was published in Lancet a few months ago. There's several other LEGEND studies that are either published or in the works. So briefly, this is in the context of a collaboration called Odyssey. So the Odyssey is a community. It's a global community that is basically studying these kinds of analysis and trying to come up with better methods for generating more reliable evidence from large-scale healthcare data. Next slide, please. There are about a couple of thousand people around the world who are active in Odyssey. There are dozens and dozens of working groups within Odyssey. There are Odyssey symposia in ordinary times. In Europe, in the US, in Asia, there are sections all over the world. Odyssey members, many Odyssey members have clinical data. They sit on data. The union of those databases has about 700 million patients in the databases. So conceivably, you can do an analysis with about 10% of the world's population and growing. The reason why this club is so to speak, how I think of Odyssey, is growing rapidly and gathering such steam is a common data model. So we have developed something called the OMOP common data model. All of these databases, it's now around 100 databases around the world, have been mapped to the common data model so that you can write an analysis, implement an analysis. There's a huge open source library to help you do that the community has developed, and deploy it anywhere in the world on any of these databases that has been mapped to the OMOP common data model. Next slide, please. Briefly, the community is looking at population level estimation. That's what I just talked about. But there's also a huge amount of activity related to patient level prediction, personalized medicine, if you will, precision medicine in these databases. And also a lot of very interesting work going on in clinical characterization, trying to understand the practice of healthcare now that we have data on this kind of scale. A quick mention of COVID. This kind of asset, if you will, and network around the world is tailor-made for studying things that are where you want to do rapid, large-scale studies. So the community has developed an outpouring of papers using the Odyssey network studying COVID. And these are just a few of them here that have been produced in short order. Next slide. So finally, what I'm really talking about here is the power of an international community and a truly global data network. I believe that we are using it to generate real-world evidence, in a much more reliable. We're not, this isn't the last word, but I do believe it's more reliable and certainly reproducible than the classical artisanal approaches. The common data model here can't be underestimated in terms of the power. You can't do this kind of science without a common data model. Obviously, if you had to write the code 100 times for 100 different databases, you're dead in the water. It can't happen. So the power of the common data model is absolutely amazing in terms of advancing science in this area. But needless to say, much work remains to be done. I invite anyone listening to this to go to the Odyssey website and join. Just join means just sign on to one of the working groups or the forums or whatever. It is an open and welcoming scientific community. Thank you very much.
Thank you very much, David. I'm a big fan of this thread of work, and I think the idea of negative control hasn't been leveraged enough really in any area of science or industry where wild predictions abound, coming from complex databases. So thank you for reminding us on that. It's not just used for estimation, but I guess a more reliable model is also better, more generalizable and, better for other sample predictions, I imagine. Right? Okay, so we did receive a number of questions, but unfortunately we are running out of time for this panel. So I will just say, on behalf of Temple University, the Department of Statistical Science, the Fox School of Business, our partners at Wells Fargo, thank you very much to Nicholas, Bean, and David for presenting our perspectives here today. Thank you for your time. Really appreciate that. Thank you.
Thank you. Thank you very much.